In this third video of the Analog Electronics Lab, we shall see a few more circuits. So these are transfer characteristics to be obtained. So we are asked to design and demonstrate a circuit diagram to obtain the following transfer characteristics. Here the transfer characteristics is a constant 3 volt line till the input voltage is 3 volt. As the input voltage exceeds 3 volts, we are supposed to get a slope of 1. So this is a corresponding circuit diagram which can give this transfer characteristics. So no need to explain the working of this one. So since we are assuming a diode drop of 0.6, so this battery should have a voltage of 3.6, so that 3.6 minus of 0.6 happens to be 3 volts when the diode is conducting. Similarly, for the second transfer characteristics, the output voltage is 0 till the input voltage is 600 millivolt and minus 600 millivolts, and it should follow the input voltage. If it is more than that, of course there's a reduction of the output voltage by 0.6, and there is an increase of output voltage by 0.6. So depending on whether it is in positive half cycle or negative half cycle. So we have this is a circuit diagram, and it should comfortably give this transfer characteristics. And this is the third transfer characteristics, which is slightly different from the previous two. Now we can see we have two batteries. So this is 3 volt, which is making your output voltage less than the input when the diode is off. And you can see this is minus 2 volt. So the output voltage is minus 2 volt when the diode is on. So when the diode is on, it is one battery that is coming into picture, and there is one more battery coming into picture when the diode is off. Now actually, while conducting this particular experiment, so this 3 volt battery has to be derived from an external power supply, whereas this 1.4 volt battery can be derived from the analog discovery itself. So when we're actually using this external battery, so care should be taken that the ground of the external battery should not be connected to this ground. So I'm repeating, this ground should not be connected to this. So there should not be connection existing between this ground and this point here. So this is exclusively connected between the resistor and the diode point. So this should never be connected to this. If you connect this, now this becomes like a short circuit. The output will be like always 0 volts. So we will not get the proper expected transfer characteristics. Sorry, all these are transfer characteristics. So this way we can comfortably do this experiment. Now we shall see now some amplifier designs. So this is, we are asked to design and demonstrate a circuit. So we are asked to design and demonstrate a circuit to obtain the following specification. Expected gain is 60 from a power supply of 5 volt, and we are assuming a collector current of 1 milliampere. And with these assumptions, like okay, beta to be 100 and reverse saturation current of the transistor to be 1 into 10 to minus 13 ampere, and the current flowing through this is actually 10 times that of the base current. So if at all, if you are using RE, you can assume a V of 100 millivolt, otherwise you can neglect it. So this is of course we can get this gain of 60 volt in many different ways. So one of the possible ways, without having that RE, the equation happens to be the VB expression is thermal voltage multiplied by the natural log of ratio of the IC by IS, which gives 598 millivolts. And we can also write the expression for VBE using this potential divider as VCC into R2 by R1 plus R2, which can also be written in the form of the current flowing through this series resistors R1 R2, which we assume it as I1 into R2. So using these values of now this I1 is actually 10 times IB. So actually IB is IC divided by beta, which is 0.1. So it is actually 10 microampere is the value of IB. So I1 happens to be 100 microampere. So using those values, we can actually get the value of R2 as 5.98 kilo ohm and R1 as 44.02 kilo ohms. Actually R1 plus R2 happens to be 50 kilo ohms. So once we know that is 50 kilo ohms, and we can certainly subtract 5.98 from 50 kilo ohms, so which comes out to be 44.08 kilo ohms. Or substituting 5.98 here, we can certainly get the value of R1 as 44.98. Sorry, 44.02 kilo ohms. And we are supposed to find the value of RC also, because the value of voltage gain required is 60. With the value of GM given by IC by VT is equal to 0.038 Siemens, the RC comes out to be 1.56 kilo ohms. So using these equations, the obtained values of components are these things. R1 is this, R2 is this much, and RC is coming out to be this. Now, since these are not the standard values, we can go for the nearest possible standard value, and we can choose the values as R1 as 47K and R2 as 5.6 and RC as 1.5 kilo ohms. And we can use a coupling capacitor of 0.1 microfarad. So after using these values, we have to actually check for the collector voltage, whether the collector voltage is as per our desired value or not. Because we are assuming a current of 1 milliampere to flow through the transistor with a value of RC as 1.5 kilo ohms. So there's a drop of 1.5 volts, meaning in this circuit we have 5 volts at the VCC, and if 1 milliampere current is flowing, so since the value of RC is 1.5K, so there's a 1.5 volt drop happens here. It is 5 minus 1.5 happens to be 3.5 here. So we are supposed to get a 3.5 volts DC voltage at the collector point. If it is 3.5, then it is fine. If it is not close to 3.5, then we have to change the value of R2 so that we can get it close to 3.5. And after getting the DC voltage of 3.5, we can apply a suitable sine wave. I can see the word suitable given because we have to apply an input voltage at that output is undistorted, and we have to have a proper gain also. So all these equations, whatever we used, is obtained from a small signal model, which is valid for midband frequency, so that the sine wave should be operating in a frequency midband range, which is around more than 5 kilohertz and less than 500 kilohertz. So you can keep frequency somewhere around 30 kilohertz, 50 kilohertz, or 100 kilohertz, and let the amplitude be in terms of hundreds of millivolts, and observe the waveform so that it is undistorted. So once we get that undistorted waveform, we can actually tabulate the values. So this VC is the collector DC voltage. AC is obtained using this expression. This is your transconductance, which you can get it using the equation IC by VT. The corresponding AV, we can get it measured from that AD kit, which is output peak to peak by input peak to peak. And you can also verify that with the theoretical value, which is GM into RC. We can also find its decibel values by 20 into log of that gain. So second choice would be the same design can be obtained using the second circuit, choice 2, where we are using emitter degeneration resistance, so that this is going to have a better stability than the previous circuit, because this gives a negative feedback, so that the output voltage, the circuit remains in stable condition against the variation in the temperature. So now you can see the major changes here. The Vx happens to be Vb plus Ve. So V is assumed to be 100 millivolt. The corresponding values of R1, R2 are given over here. The value of RC is calculated using this, and these are the design values. These are the nearest possible design values. We'll be actually using these as the values of R1, R2, RC, and the coupling capacitor, as well as the bypass capacitor. So bypass capacitor is used so that it can provide an easy path for your AC signal at midband frequencies. So that's why it is a bit higher value. And once we are through with the connections, we have to actually check for the DC condition. If it is 3.5 at the collector point, it is fine. Otherwise, we have to change the value of R2 so that we get a proper gain. Again, a similar type of readings as we explained in the previous case. Now here it is design and demonstrate a circuit with a voltage gain far greater than 1 and okay, here the condition is you are supposed to obtain maximum swing. So output voltage should be having maximum swing. So these are the specifications, and here we have this is a possible circuit, and since it is we are supposed to have a maximum output voltage swing. So here if you just consider this as available swing 0 to 5 as available swing, and this is 0.2 to keep this transistor in saturation. The left out voltage is 4.8, so half of 4.8 happens to be 2.4. If you take if you subtract 2.4 from 5, so this happens to be 2.6, meaning the collector voltage should be at 2.6, so that it the output voltage will have a maximum swing. So to have the collector voltage at 2.6 with a collector current of 1 milliampere, we are supposed to have the value of RC to be 2.4 kilo ohms. So that's why it is given over here. Using this expression, VC is equal to VCC minus ICRC. So which you can easily get this expression over here. And this is now 2. RC approximately 2.4 kilo ohms. And the other values are fine as in the previous case. The R2 happens to be 5.98 and R1 is 44.02, and the gain comes, of course, is not actually 100k, it's actually 1 over 26 multiplied by 2400, so this is slightly less than 100. And once we are through with these design values, we have to choose the nearest possible standard values, which are over here. So once you're if it is close to 2.6, it's fine. Otherwise, if it is not so, then you have to change the value of R2 so that it is 2.6, so that you can get maximum available swing of the circuit. The readings as explained in the previous case. We shall look into this in the next video.